So guys, in the video we have seen what do you mean by as an optical isomerism and what do you mean by enantiomers. So now we are going to see that how to calculate the number of the optical isomers if depending upon the number of your chiral carbons. So basically there is a formula to calculate number of optical isomers. So which is depend upon which one? Number of chiral carbon atoms. What's that? Chiral carbon atoms. Basically the formula is given as 2 to the power of n, where our n represents your number of chiral carbon atoms. Let us take an example. So basically I am going to take an example of CH3, CH, Cl, CH, Br, CH3. So of course when we are observing this structure, we could see that this carbon, so yes, in this structure we could see that this carbon is also surrounded by the 4 different groups. I can consider this one as the first group, this one as the second group, overall this one as my third group, and this one as my fourth group. And also similarly when I consider this carbon, this could be considered the first group, second group, third group, and the fourth group. So overall these molecules are having the 2 chiral carbons. Alva? So illivarige navin nodidvi, these molecules were having a single chiral carbon. And we also said as what an important note, whenever your molecule is having a single chiral carbon, of course and 100% sure they will be optically active. But now when the question arises when they are having the 2 carbon centers, chiral carbon centers, whether they are optically active or not. Yes, they are optically active. How we can say they are optically active? So when you are considering this carbon and this carbon, they are not having any plane of symmetry. But when the question arises that what is the number of the optical isomers possible, alva? One chiral carbon iddaga navu ಏನು ನೋಡಿದ್ವಿ, ಒಂದು D and L form 2 isomer ನ ನೋಡಿದ್ವಿ ಪ್ರತಿ ಒಂದು ಸ್ಟ್ರಕ್ಚರ್ ಗೆ. So ಇಲ್ಲಿ ನಾವು ನೋಡಬೇಕು ಅಂದ್ರೆ ಏನು ಮಾಡಬೇಕು ಈಗ? We have to use this formula. What does this n signifies? The number of your chiral carbon. Since in this structure we are having the 2, alva? 2 chiral carbons are there. So ಇಷ್ಟು possibilities ಇರುತ್ತೆ, 2 to the power of 2, that is equals to 4. If someone asks you to write its structure, so how can we write it? First let us write one structure. Now overall molecule na consider ಮಾಡಬೇಕಲ್ವಾ, ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ 2 chiral carbons untu and it's a bulk molecule. So here comes your CH3, here is your Cl, here is your H, okay, C, H, and here I can write my Br and that of your CH3. This is first structure. ಫಸ್ಟ್ ಸ್ಟ್ರಕ್ಚರ್ ಬರೆದುಕೊಳ್ಳಿ, ಅದರದ್ದು ಒಂದು ಮಿರರ್ ಇಮೇಜ್ ಬರ್ಕೊಬಿಡೋಣ. ಯಾವ ತರ ಬರುತ್ತೆ? CH3 ಇದೇನಾಗುತ್ತೆ, Cl ಈ ಕಡೆ ಬರಬೇಕು, ಈ H ಈ ಕಡೆ ಹೋಗುತ್ತೆ. ಅದೇ ರೀತಿ ಈ Br ಏನಾಗುತ್ತೆ, ಈ ಕಡೆ ಬರುತ್ತೆ, ಈ H ಈ ಕಡೆ ಹೋಗುತ್ತೆ. ಇದೇನಾಯ್ತು, 2 ಐಸೋಮರ್ ಸಿಕ್ತು. ಇನ್ನೂ 2 ನಮಗೆ ಬೇಕು. ಸೊ ಅದು ಯಾವ ತರ ಇರಬಹುದು ಅಲ್ವಾ? ಇಲ್ಲೇನ್ ಮಾಡಿದೀವಿ ನಾವು ಅಂದ್ರೆ H ಮತ್ತೆ H ನ ಒಂದೇ ಕಡೆ ಬರ್ಕೊಂಡಿದೀವಿ. ಸೊ ಲೆಟ್ ಅಸ್ ರೈಟ್ ಪಾಸ್ ಒನ್ ಮೋರ್ ಸ್ಟ್ರಕ್ಚರ್ ಇನ್ ದಿಸ್ ವೇ. CH3, H, Cl, C, illen barkobodu, Br. Okay, I'm just, this part is over. Okay, now I'm writing one new structure, possible structure. And here I will write it as a H, so here CH. So this structure's mirror image, how it would be? Yes, CH3, Cl, H, CH, Br, CH3. So can you see all these structures are somewhat different, they are unique. So yes, 2 optical isomers there are literally 1, 2, 3, 4, and that is what we have obtained over here. And one more important thing, can we see anywhere a plane of symmetry? Of course not. What does it signifies then? Yes, whatever the structures we have written, all the 4 structures are optically active. Able to understand? So what about you can say first and the second, third and fourth, alva? So can I say first and the second as enantiomers? Of course yes, because the two structures are mirror images of one another and they are not superimposable alva. Ee structure na idu mele ittaga enagutte, they are not coinciding with respect to the similar atoms alva. They are not superimposable. Since the two optical isomers are non-superimposable mirror images, first and second can be called as what? Enantiomers. Similarly, what you can say with respect to third and fourth alva, e structure matte e structure mirror images, they are optically active and also what? They are non-superimposable mirror images. E structure na hinge hogi iದ್ರ ಮೇಲೆ ಇಟ್ಟಾಗ ಏನಾಗುತ್ತೆ? They will not coincide alva. Cl ಮೇಲೆ ಕೂರಲ್ಲ, ಇನ್ಸ್ಟೆಡ್ ಏನಾಗುತ್ತೆ Cl ಹೋಗಿ H ಮೇಲೆ ಕೂರುತ್ತೆ, H ಏನ್ ಮಾಡುತ್ತೆ Cl ಮೇಲೆ ಕೂರುತ್ತೆ. So like that is called as what? Non-superimposable. So third and fourth are also what? Enantiomers. ಬರೀಬಹುದಲ್ವಾ? ಹಾಗಾದ್ರೆ ಈಗ ಒಂದು ಡೌಟ್ ಆಗುತ್ತೆ, ಒಂದೇ ಸ್ಟ್ರಕ್ಚರ್ ಅಲ್ಲಿ ನಮಗೆ ಒಂದೇ ಕಾಂಪೌಂಡ್ ನಮಗೆ 4 ಸ್ಟ್ರಕ್ಚರ್ ಸಿಕ್ತು. ಆಯ್ತು ಸರ್, ಫಸ್ಟ್ ಸೆಕೆಂಡ್ ಎನಾನ್ಶಿಯೋಮರ್ಸ್, ಥರ್ಡ್ ಫೋರ್ತ್ ಎನಾನ್ಶಿಯೋಮರ್ಸ್. ಹಾಗಾದ್ರೆ ಫಸ್ಟ್ ಮತ್ತೆ ಥರ್ಡ್ ಏನು ಅಲ್ವಾ? ಫಸ್ಟ್ ಮತ್ತೆ ಫೋರ್ತ್ ಏನು? ಅದೇ ರೀತಿ ಫಸ್ಟ್ ಮತ್ತೆ ಸೆಕೆಂಡ್ ಮತ್ತೆ ಥರ್ಡ್ ಏನು? ಅದೇ ರೀತಿ ಸೆಕೆಂಡ್ ಮತ್ತೆ ಫೋರ್ತ್ ಏನು ಅಲ್ವಾ? ದಿಸ್ ವಿಲ್ ಬಿ ನಾರ್ಮಲ್ ಕ್ವಶನ್. ಯಾಕಂದ್ರೆ ಒಂದೇ ಕಂಪೌಂಡ್ ತಗೊಂಡಾಗ ನಮ್ಗೆ ಈ ತರ ಸ್ಟ್ರಕ್ಚರ್ಸ್ ಬರ್ತಾ ಉಂಟು. ಯಾವುದು 2 ಸ್ಟ್ರಕ್ಚರ್ ತಗೊಂಡು ನಾವು ಎನಾನ್ಶಿಯೋಮರ್ಸ್ ಅಂತ ಹೇಳಿದಾಗ ಇನ್ ಮಿಕ್ಕಿ ಸ್ಟ್ರಕ್ಚರ್ಸ್ ನ ಏನಂತ ಕರಿಬೇಕು? ರಿಮೆಂಬರ್, ದೀಸ್ 4 ಪಾಸಿಬಿಲಿಟೀಸ್ ಆರ್ ಕಾಲ್ಡ್ ಆಸ್ ಡಯಾಸ್ಟೀರಿಯೋಮರ್ಸ್. ಏನಂತ ಹೇಳ್ತೀವಿ ನಾವು ಇದನ್ನ? ಡಯಾಸ್ಟೀರಿಯೋಮರ್ಸ್. Then how can you define this diastereomers? Yes, so they the sets of isomers. ಏನಂತ ಹೇಳ್ಬೋದು ನಾವು? Diastereomers are what? They are the sets of isomers which are not the mirror images of each other. ಹೇಳ್ಬೋದಲ್ವಾ? So ಇದನ್ನ ಮತ್ತೆ ಇದನ್ನ ಕನ್ಸಿಡರ್, they are not the mirror images ಅಲ್ವಾ, but they are set of isomers. So ಯಾವ ತರ ನಾವು diastereomers ನ ಹೇಳ್ಬೋದು? They are the set of isomers which are not the mirror images of one another, which are not the mirror images of one another. Mirror images ಆಗಿಲ್ಲ ಅಂದ್ರೆ ಏನಂತ ಅರ್ಥ? ಅವು ಅದೇ ಸ್ಟ್ರಕ್ಚರ್ ಆಗಿರ್ಬೇಕು. ರಿಮೆಂಬರ್, ಆ ಕಂಪೌಂಡಿನ ಸ್ಟ್ರಕ್ಚರ್ ಅಲ್ಲೇ ನಾ ಮಾತಾಡ್ತಾ ಇದ್ದೀನಿ ಅಲ್ವಾ? ಕಂಪೌಂಡ್ ತಗೊಂಡಿದ್ದು ಯಾವುದು? ಈ ಕಂಪೌಂಡ್ ನಾನು ತಗೊಂಡೆ. ಸೊ ಈ ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ ನ ಕನ್ಸಿಡರ್ ಮಾಡಿದಾಗ ಏನಂತ ನೋಡ್ತಿದ್ದೀನಿ, ನಂಗೆ 4 ಪಾಸಿಬಲ್ ಸ್ಟ್ರಕ್ಚರ್ಸ್ ಉಂಟು. ಈ 4 ಪಾಸಿಬಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಹೌದೋ ಅಲ್ಲ ಅಂತ ಹೆಂಗ್ ಗೊತ್ತಾಯ್ತು? ನಂಗೆ ಯಾವುದೋ ಒಂದು ಸ್ಟ್ರಕ್ಚರ್ ಅಲ್ಲೂ ನಂಗೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇಲ್ಲ. ಸೊ ಇಫ್ ದೇರ್ ಇಸ್ ನೋ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿ, ವಾಟ್ ಐ ಕ್ಯಾನ್ ಸೇ? Of course, all the 4 structures are optically active. And also further I dealt with it what? I know the concept of enantiomers. So I came to know that if the 2 isomers are non-superimposable mirror images, I repeat, if the 2 isomers are non-superimposable mirror images, they are called as an enantiomers. And I came to know there are 2 such enantiomers are existing. But when the question arises, what about the first and the third structure, first and the fourth structure, third and the second structure, and second and the fourth structure? Totally there are 4 possibilities other though. So what are these called as? So they are called as a diastereomers. Then what do you mean by this diastereomers? So they are the set of isomers which are not, what it is? Which are not the mirror images. ಅವು ಮಿರರ್ ಇಮೇಜಸ್ ಆಗಿರೋದಿಲ್ಲ. ಸೊ ಆ ತರ ಒಂದು ಸ್ಟ್ರಕ್ಚರ್ಸ್ ನಾವು ಏನಂತ ಹೇಳ್ತೀವಿ? ಡಯಾಸ್ಟೀರಿಯೋಮರ್ಸ್. ಕೂಲ್? Able to understand? So enantiomers and diastereomers. So we came to know in today's video importantly 4 important and interesting facts. What were those? First and the foremost thing, what do you call as an optical isomerism? Alva. The second most important thing, what are the criteria for a molecule to exhibit that of your optical activity? And we came to know the main criteria is the molecule should not contain any plane of symmetry. Then the third most interesting fact we came to know, an important note, whenever a molecule is having just one chiral carbon, of course, those molecules will be optically active. ಅಲ್ವಾ? ಯಾಕಂದ್ರೆ ಒಂದೇ ಕಾರ್ಬನ್ ಇರುತ್ತೆ, ಅದ್ರ ಮೇಲೆ 4 ಡಿಫರೆಂಟ್ ಗ್ರೂಪ್ಸ್ ಇರುತ್ತೆ, ಯಾವ ತರದ್ದು ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿನೂ ಇರಲ್ಲ. ಆ ಕಾರಣದಿಂದ ಅದೇನಾಗಿರುತ್ತೆ? ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಆಗಿರುತ್ತೆ. Then we came to know the 2 interesting definitions called as that of your enantiomers and diastereomers. Enantiomers means what? 2 isomers which are non-superimposable on their mirror images, whereas diastereomers are the set of isomers which are not the mirror images of each other. Enantiomers ಏನಾಗುತ್ತೆ? ಮಿರರ್ ಇಮೇಜಸ್ ಆಗಿರುತ್ತೆ, ಆದ್ರೆ ಆ ಮಿರರ್ ಇಮೇಜಸ್ ಒಂದ್ರ ಮೇಲೆ ಒಂದು ಕೂರೋದಿಲ್ಲ. Whereas diastereomers ಏನಾಗಿರುತ್ತೆ ಅವು ಮಿರರ್ ಇಮೇಜಸ್ ಆಗಿರೋದೇ ಇಲ್ಲ. Able to understand? They are not the mirror images. So those set of isomers are called as what? Diastereomers. Let us take one more example of now tartaric acid. Tartaric acid. ಎಲ್ಲಿರುತ್ತೆ tartaric acid? Tamarind, ಹುಣಸೆ ಹುಳಿ ಇರುತ್ತಲ್ಲ ಅದರ ಒಂದು ಆಸಿಡ್ ಯಾವುದು? Tartaric acid. So if I am going to take the structure will be written in this way. COOH, acid ಅಂತ ಉಂಟಲ್ವಾ, COH group ಇರಲೇಬೇಕು. CHOH, similarly CHOH, and here you are going to get as COH. Now can you please say me what will be the number of your chiral carbons over here? I repeat, what is the number of the chiral carbon over here? Alva? So this is one chiral carbon, this is another chiral carbon. So we are having the two chiral carbons in the tartaric acid. Can you please suggest what will be the number of the optical isomers? Number of optical isomers ಎಷ್ಟಿರುತ್ತೆ ಸಾಧ್ಯ? ನನ್ನ ರೂಲ್ಸ್ ಪ್ರಕಾರ, ಫಾರ್ಮುಲಾ ಪ್ರಕಾರ 2 to the power of n ಅಂದ್ರೆ 2 square, which is equals to 4. Yes. Now the question arises. So whatever I have written, optical isomer, whether all the 4 isomers are optically active, ಹೌದೋ ಅಲ್ವೋ ಅಂತ ಈಗ ನೋಡೋಣ. Okay. So now let us write it. How will I write the structure? COOH, COOH. Yes, then here I will be getting as what? OH, here one H, similarly here one H, and here one OH. Can you see? So this is one structure. Another optical isomer yavutar irbodu, it's mirror image. So here I will be writing as COOH. Here I will be having as OH. Here I will be having as H. Whereas here you will be having as set of your OH. And here I will be having as H. And here COOH. After writing the structure, you have to see whether they are having any plane of symmetry. Of course not. Any plane in any direction, if I am going to draw my plane, I am not going to divide this molecules into 2 equal halves. So I have got the 2 isomers. But there are how many isomers? 4 isomers. So what are the other possibilities of the structures I can write? Yes, COOH. Alva, here one C, here one C, and here COOH. Another possibility was this one H and an H. Here OH and an OH. Another part COOH. Yes, here what I can write? OH, H. Here I can write as what? Yeah, please, H, OH. Here COOH. So now this is your first, second, third, and the fourth structure. So what you can see in the first and the second structure, there is no plane of symmetry. Can you say the same thing for the third and the fourth? But there is a plane of symmetry for this structure. Are you able to see? So when I am going to put a plane over here in this way, what will be happening? You are going to divide the molecule into 2 equal halves in the third and the fourth structure. So there is a possibility. Okay, it's an exception case. So whenever we are putting this formula, it is not necessary that it is giving us a proper answer. It is only possible to know from its structure itself. Able to understand? So tartaric acid na consider ಮಾಡಿದಾಗ ಏನಾಗ್ತಾ ಉಂಟು, whenever you are having the 2 chiral carbons, there is not a possibility that all the possible 4 isomers obtained are optically active. The greatest example is your tartaric acid. First and the seconds are what? They are optically active. But when you are considering the third and the fourth, what has happened? They are optically inactive. Why is it so? Because it is having what? A plane of symmetry. Can you see this? Yes. So among these isomers, what is we can say? The first and the second images of each other form a set of your enantiomers. So this can be what? Our enantiomers. Even though isomer third, it is containing the 2 asymmetric carbon. Asymmetric carbon untu. Adu enagide molecules are having the plane of symmetry. That is the reason I have mentioned. Chiral carbon ಇದ್ದಾಕ್ಷಣನೇ ಅದು ನಾವು ಹೇಳಕ್ಕಾಗಲ್ಲ ಅದು ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಅಂತ. ಯಾವಾಗ ಹೇಳಕ್ ಸಾಧ್ಯ? ಆ ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ ಅಲ್ಲಿ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು. ಇಲ್ಲಿ ನಾವು ನೋಡಿದ್ವಿ ಕೈರಾಲ್ ಕಾರ್ಬನ್ ಉಂಟು, ಆದ್ರೂ ಕೂಡ ಇಲ್ಲಿ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಕೂಡ ಉಂಟು. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತಿದ್ದು ಆಪ್ಟಿಕಲಿ ಇನ್ಆಕ್ಟಿವ್ ಆಯ್ತು. ರಿಮೆಂಬರ್ ಗೈಸ್, your third and the fourth structure, they are called as what? As a Meso compounds. A new name one again. Alva? What it is called as, the isomers are not optically active, and these are called as what? Mesotartaric acid, or in simple words we can call it as a meso compounds. So whenever if a question arises, what is the number of the optical isomers for your tartaric acid, what will be your answer? It is only 2. Alva? Number of the optical isomers for tartaric acid is only 2. Even though it is having the 4 structures, but the first 2 structures itself, they are not having the plane of symmetry. Other 2 structures are having the plane of symmetry, so they will be optically inactive. Therefore, for a tartaric acid, number of the optical isomers are only 2. Able to understand? And we also came to know an important concept about the 3rd and the 4th structure. They are called as what? As a mesotartaric acid or a meso compounds. Then how can we define this meso compounds? Remember, the compounds containing more than one asymmetric carbon, yes, but due to the presence of plane of symmetry, what you can say, they do not show optical activity. Alva? So these are called as what? Meso compounds. Second, third, fourth, of course they are not enantiomers. Why they are not enantiomers? Because first and the foremost thing, they are not optically active. Enantiomers are defined they are the optical isomers ಅಂತ ಹೇಳಿದ್ವಿ. They are what? They are not optically active. Yake? Because they are having the plane of symmetry. So we can't call third and the fourth as a diastereomers. And we can't call them as a diastereomers. Why? Because they are the mirror images. Diastereomers they should not be the mirror images. Enantiomer antanu helakagalla because they are optically inactive. Diastereomers antanu helakagalla because they are the mirror images. So we need a name for it. So in anta name kottvi adukke we are giving it as a mesotartaric acid anta heltivi. General agi meso compounds anta heltivi. Meso compounds andre artha enu? The compounds in which you will be having more than one chiral carbon alva, asymmetric carbon irutte. Adre enagirutte, even though they are having the chiral carbon, they will be optically inactive. And what is the reason? Because they are having such plane of symmetry. So that is the reason they are called as what? Meso compounds. Is that clear? Okay. Now let us see certain reactions part. So these reactions are mainly when your nucleophile attacks the stereogenic center. What do you mean by the stereogenic center? Of course, when I was dealing with SN1 and SN2, I made use of certain words. At that moment, it would be somewhat confusing for you. So that is the reason, after explaining these terms, enantiomers, optical isomers, all those concepts, chiral carbon, now I am going to deal once again with those concepts what I have taken as an example for SN1 and SN2. So ಏನು stereogenic center andre nothing but that of your chiral carbon. So now what we are seeing is basically whenever a nucleophile is going to attack your chiral carbon directly, what are the possible reactions? What are the possibility of the reaction? Basically, we are going to understand in this concept first important thing which is called as that of your retention. And the second most important thing is called as that of your inversion. And the third most important thing which is called as your racemization. These three concepts we are going to understand now under this topic whenever your nucleophile is going to attack your stereogenic center. For example, guys, let me take this structure. CCH3Br, yes, next H, and that of over here as C2H5. Can I write it in this way? Okay. Plus OH minus. So what we are seeing over here, so this nucleophile is going to attack our stereogenic center. This is now our chiral carbon. So what is the structure I am going to get? CH3, OH, and here I am going to get as what? C2H5, and over here as H. Now I am going to say this reaction is called as what? Retention. What you can say? Whatever the reaction how it has happened, the product has been formed is with respect to the retention. Now the question arises that what do you mean by this retention? You can just see that whenever there is a nucleophilic attack to the stereogenic center, yes, or stereogenic carbon atom, the nucleophile has occupied the position of that of your leaving group, your bromide. Alva? Yelli bromide in a position itto, allige nama nucleophile bandu kootide. Whatever the position of your bromine was there, in that position itself our hydroxide ion has come and sit. So yenagide, there is no change in the configuration. Alva? There is no change in the configuration of your structure. So our reason in the yenagide, this is an example of our retention. Yav taradu bond shift agilla. Yav tara bond shift agilla. Yav bond elli irbekitu allene untu. That is called as what? Retention. Alva. So now if I am going to take an example for inversion, let us explain you in this way. So let me take a CBr, yes, a CH3, C6H5, and over here as I'm going as H. So now here what happens, whatever your nucleophile is there, it is going to attack your stereogenic center from opposite side of your leaving group. Yenagta untu yena ನಿಮ್ಮ nucleophile attack untala, it is going to attack our stereogenic center from opposite side from that of your leaving group. ಹಾಗಾದಾಗ ನಮಗೆ ಸ್ಟ್ರಕ್ಚರ್ ಯಾವ ತರ ಸಿಗುತ್ತೆ? It will be in this way. COH, CH3, ಏನಾಗಿದೆ H, and over here I am getting as what? C6H5 plus Br minus. Can you please see both the structures? ಇಲ್ಲೇನಾಯ್ತು, ಬ್ರೋಮಿನ್ ಪೊಸಿಷನ್ ಅಲ್ಲೇ ನಮ್ಮ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಅಟ್ಯಾಕ್ ಆಗಿದೆ. Whatever the position of your bromine was there, there itself our nucleophile has come and sit in our retention. Whereas in that of your inversion, what we are saying, where the bromine was there, to its opposite side our OH has come and sit. Alva? So there is an inversion of the configuration. Are you able to understand? Very much important state. ಇದನ್ನ ನಾನು SN2 mechanism ಅಲ್ಲಿ ನಿಮಗೆ ಅರ್ಥ ಮಾಡಿಸಿದ್ದೆ ಅಲ್ವಾ? The same example I have took over here. You have to just remember one important thing, guys. What is that? Whenever our OH minus is coming and attacking from the opposite side of your leaving group, we will be obtaining a transition state. What we will be obtaining? A transition state will be obtained. As the nucleophile is getting closer to the carbon atom, the leaving group moves away from the stereogenic carbon. Alva? For example, let me write a general case. CBr like this and like this. So our OH minus is attacking from the back side. So first ಏನಾಗುತ್ತೆ, ಒಂದು ಟ್ರಾನ್ಸಿಷನ್ ಸ್ಟೇಟ್ ಅನ್ನೋದು ಸಿಗುತ್ತೆ. ಸೊ ಆ ಟ್ರಾನ್ಸಿಷನ್ ಸ್ಟೇಟ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಟೋಟಲ್ ಆಗಿ ಕಾರ್ಬನ್ ಸುತ್ತಮುತ್ತ 5 ವೇಲೆನ್ಸಿ ಇರುತ್ತೆ, ವಿಚ್ ಇಸ್ ಹೈಲಿ ಅನ್ಸ್ಟೇಬಲ್. ಆದ್ರೂ ಕೂಡ ಅದು ಫಸ್ಟ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗಿರುತ್ತೆ. ದಿಸ್ ಇಸ್ ನಾಟ್ ಎಕ್ಸ್ಟ್ರಾಕ್ಟೇಬಲ್. ಇದನ್ನ ನಾವು ಎಕ್ಸ್ಟ್ರಾಕ್ಟ್ ಮಾಡಕ್ ಆಗಲ್ಲ. ಬಟ್ ಆಲ್ಸೋ ಇಟ್ ವಿಲ್ ಬಿ ಪ್ರೆಸೆಂಟ್ ಇನ್ ದಿ ಸಿಸ್ಟಮ್ ಫಾರ್ ಅ ಶಾರ್ಟ್ ಪೀರಿಯಡ್ ಆಫ್ ಟೈಮ್. ಇದು ಒಂದು ಏನಾಗುತ್ತೆ, ಟ್ರಾನ್ಸಿಷನ್ ಸ್ಟೇಟ್ ಆಗಿರುತ್ತೆ. ಈ ಟ್ರಾನ್ಸಿಷನ್ ಸ್ಟೇಟ್ ಅಲ್ಲಿ ಏನಾಗಿದೆ, ಬ್ರೋಮಿನು ಇರುತ್ತೆ, ನ್ಯೂಕ್ಲಿಯೋಫೈಲು ನಮ್ಮ ಸ್ಟೀರಿಯೋಜೆನಿಕ್ ಸೆಂಟರ್ಗೆ ಅಟ್ಯಾಕ್ ಆಗಿರುತ್ತೆ. ನೆಕ್ಸ್ಟ್ ಏನಾಗುತ್ತೆ, ಆಸ್ ದ ಟೈಮ್ ಪ್ರೊಸೀಡ್ಸ್, ದ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಮೇಕ್ಸ್ ಅ ಸ್ಟ್ರಾಂಗ್ ಬಾಂಡ್ ವಿತ್ ದ ಸ್ಟೀರಿಯೋಜೆನಿಕ್ ಸೆಂಟರ್, whereas the bromine or the bromine whatever is leaving group is there, that is going to leave our stereogenic center. But it is not going to leave as such. In turn, what it is going to do, soon after it is leaving, the other 3 groups whatever is present, I repeat, whatever the other 3 groups are present on the stereogenic center, they will also move towards the direction of your leaving group. ಏನಾಗ್ತಾ ಉಂಟು, ಲೀವಿಂಗ್ ಗ್ರೂಪ್ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಬಿಟ್ಟು ಹೋಗುತ್ತೆ ಅಲ್ಲ, ಅಲಾಂಗ್ ವಿತ್ ದಿ ಬಾಂಡ್ ಇಟ್ ಇಸ್ ಮೂವಿಂಗ್ ಔಟ್. ಆದ್ರೆ ಇನ್ನು 3 ಬಾಂಡ್ಸ್ ಏನಿತ್ತಲ್ವಾ, ಅದೇನಾಗುತ್ತೆ, ಇಟ್ ವಿಲ್ ಸ್ಲೈಟ್ಲಿ ಮೂವ್ ಟುವರ್ಡ್ಸ್ ದಿ ಲೀವಿಂಗ್ ಗ್ರೂಪ್ ಇನ್ ಪೊಸಿಷನಿಂಗ್ ಸ್ವಲ್ಪ ಶಿಫ್ಟ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಇಟ್ ವಿಲ್ ಬಿ ಜನರಲಿ ಯು ವಿಲ್ ಬಿ ಹ್ಯಾವಿಂಗ್ ಲೈಕ್ ದಿಸ್ ಸ್ಟ್ರಕ್ಚರ್, ಈ ತರ ಬರುತ್ತೆ. Can you see the shifting of these three bonds? ಇಲ್ಲಿ ಬ್ರೋಮಿನ್ ಇತ್ತಲ್ಲ, ಈ ಬಾಂಡ್ ಎಲ್ಲ ಏನಾಗುತ್ತೆ, they are also moving in the direction of your leaving group. So this part is called as what? As an Walden inversion. ಏನಂತ ಹೇಳ್ತೀವಿ? The final product whatever we have obtained is to the phenomenon of your Walden inversion. Very much important. So ಏನಿದು Walden inversion ಅಂದ್ರೆ, so during a chemical reaction, if the product which has been formed has an opposite configuration to that of the reactant, then the phenomenon is called as what? Inversion of configuration, and this is also known as what? As an Walden inversion. ಅರ್ಥ ಆಗ್ತಾ ಉಂಟಾ? ಏನಾಯ್ತು, OH ಮೈನಸ್ ಬಂದು ಬ್ಯಾಕ್ ಸೈಡ್ ಇಂದ ಬಂದು ಅಟ್ಯಾಕ್ ಆಯ್ತು ಸ್ಟಿರೋಜೆನಿಕ್ ಸೆಂಟರ್ ಮೇಲೆ. We are getting a transition state with both our nucleophile as well as that of your bromine group is present, but after a shorter period of time what happens? The OH gets permanently bonded with your stereogenic center, and the other three groups are they are moving towards the top of your leaving group. So that is part we are called as what? This inversion of the configuration will be called as your Walden inversion. ಇದು ಹೇಳಿದ್ದೆ ನಾನು. ಇದು ಯಾವ ತರ ಕಾಣುತ್ತೆ ಅಂದ್ರೆ, when you are going in a very ತುಂಬಾನೇ ಜೋರ್ ಗಾಳಿ ಬೀಸ್ತಾ ಉಂಟು, you have took your umbrella, a storm weather, rainy storm. ಸೊ ಅವೇನಾಗುತ್ತೆ, ಒಳಗಡೆ ಇಂದ ಏರ್ ನುಗ್ದಾಗ ಅಂಬ್ರೆಲಾ ಟರ್ನ್ ಆಗುತ್ತಲ್ವಾ, ಹ್ಯಾಂಡಲ್ ನಿಮ್ ಕೈಲಿ ಇರುತ್ತೆ, ಅದೇ ಮೇಲ್ಗಡೆ ಅಂಬ್ರೆಲಾ ಏನಾಗುತ್ತೆ, ಟರ್ನ್ ಆಗ್ಬಿಡುತ್ತೆ. ದ ಸೇಮ್ ಕಾನ್ಸೆಪ್ಟ್ ಯು ಆರ್ ಸೀಯಿಂಗ್, ಟರ್ನಿಂಗ್ ಆಫ್ ಯುವರ್ ಅಂಬ್ರೆಲಾ ಡ್ಯೂರಿಂಗ್ ದ ವಿಂಡ್ ಸ್ಟಾರ್ಮ್. ಅದೇ ಸ್ಟ್ರಕ್ಚರ್. ಈ ಸ್ಟ್ರಕ್ಚರ್ ನ ಕನ್ಸಿಡರ್ ಮಾಡಿಕೊಂಡ್ರೆ ಈ ಸ್ಟ್ರಕ್ಚರ್ ಆಗಿರುತ್ತೆ. ಆದ್ರೆ SN2 ಮೆಕ್ಯಾನಿಸಮ್ ಆದ್ಮೇಲೆ ಏನಾಗುತ್ತೆ, ದಿಸ್ ವಿಲ್ ಬಿ ಇನ್ ದಿಸ್ ವೇ, ಲೈಕ್ ದಿಸ್. ಹ್ಯಾಂಡಲ್ ಕೆಳಗನೆ ಇರಬೇಕು, whereas this structure will be topsy-turvy. It will be ulta. So this is called as what? Walden inversion. When it is possible in our SN, yes please say SN2 mechanism. Okay. Since now we have seen the retention and that of your inversion. Inversion yavaga SN2 ali. ಈಗ ನಾವು racemization ಗೆ ಬರೋಣ. What do you mean by this racemization? Remember guys, as I have said when I was dealing with my SN1 condition, ಏನ್ ಹೇಳಿದೆ SN1 condition ಅಲ್ಲಿ ಒಂದು ಎಕ್ಸಾಂಪಲ್ ತಗೊಂಡಿದ್ದೆ. ಏನಂತ, CH3Br C2H5 and here I am having my H. This is I am taking as an SN1 condition. So what I am going to get, COH, yes, CH3. Here I am going to get as my H and here as my C2H5 and a plus one more structure. Enadu CH3OH. Here I am going to get as my C2H5 and here as my H plus that of your HBr. So in sikta untu nangilli I am getting a two important products. One will be our L isomer and another will be our D isomer. ಅರ್ಥ ಏನು, ದ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಇಸ್ ಅಟ್ಯಾಕಿಂಗ್ ಅವರ್ ಸ್ಟಿರೋಜೆನಿಕ್ ಸೆಂಟರ್, ಒನ್ ಅಬೌವ್ ದಿ ಪ್ಲೇನ್ ಅಂಡ್ ಅನದರ್ ಬಿಲೋ ದಿ ಪ್ಲೇನ್. ಸೊ ಆ ತರ ನಮ್ಗೆ ಎರಡು ಮಿಕ್ಸ್ಚರ್ ಸಿಗ್ತಾ ಉಂಟು. ಸೊ ದಟ್ ಪ್ರೊಸೆಸ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ವಾಟ್ ಯುವರ್ ರೆಸಿಮೈಸೇಷನ್. ಏನಂತ ಹೇಳ್ಬೋದು ನಾವು, ದ ಫೆನಾಮಿನನ್ ಆಫ್ ಕನ್ವರ್ಷನ್ ಆಫ್ ಎನ್ ಎನಾನ್ಶಿಯೋಮರ್. ಏನು ರೆಸಿಮೈಸೇಷನ್ ಅಂದ್ರೆ, ಫೆನಾಮಿನನ್ ಆಫ್ ಕನ್ವರ್ಷನ್ ಆಫ್ an enantiomer into a racemic mixture, during the reaction, yes, that phenomenon will be called as what? Your racemization alva. So ಒಂದು enantiomer na ಏನ್ ಮಾಡ್ತೀನಿ, ರೆಸಿಮಿಕ್ ಮಿಕ್ಸ್ಚರ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡ್ತಿದ್ದೀನಿ ಅಂದ್ರೆ ಅರ್ಥ ಏನಾಗುತ್ತೆ, ಆ ಒಂದು ಫೆನಾಮಿನನ್ ಏನಂತ ಕರೀಬಹುದು, ರೆಸಿಮೈಸೇಷನ್. ಸೊ ಹೌ ವಿಲ್ ಯು ಪ್ರಿಪೇರ್ ದಟ್ ರೆಸಿಮಿಕ್ ಮಿಕ್ಸ್ಚರ್ ಅಲ್ವಾ, ಅದು ಇಂಪಾರ್ಟೆಂಟ್. ರಿಮೆಂಬರ್ ಗೈಸ್, ಸೊ ನನ್ನ ಒಂದು ಕೆಮಿಕಲ್ ರಿಯಾಕ್ಷನ್ ಮಾಡಿದಾಗ ಅರೌಂಡ್ ಯುವರ್ ಸ್ಟಿರೋಜೆನಿಕ್ ಸೆಂಟರ್ ಅಲ್ಲಿ ಎನಾನ್ಶಿಯೋಮರ್ ಸಿಗುತ್ತೆ. ಸೊ ಇಫ್ ದಿ ಪ್ರಾಡಕ್ಟ್, ಏನ್ ನಂಗೆ ಪ್ರಾಡಕ್ಟ್ ಸಿಕ್ಕಿದಲ್ಲ ಇವೆರಡು ನಾ ಏನ್ ಮಾಡ್ತೀನಿ, ಐ ವಿಲ್ ಬಿ ಕನ್ಸಿಡರಿಂಗ್ ದಿಸ್ ಒನ್ ಆಸ್ 50% this one as 50%. So overall ಏನಾಯ್ತು 100% ಆಯ್ತು. But ಏನಾಗುತ್ತೆ, ಈ 50% since it is L isomer, it will try to rotate your plane polarized light in the anti-clockwise direction. ಅದೇ polarized light ನ ಇದೇನ್ ಮಾಡುತ್ತೆ, ಅದೇ ಮಿಕ್ಸ್ಚರ್ ಅಲ್ಲಿ this will try to rotate in the clockwise direction. ಮ್ಯೂಚುವಲ್ ಆಗಿ ಎರಡು ಈಕ್ವಿಮೋಲಾರ್ ಇರೋ ಕಾರಣದಿಂದ ಏನಾಗುತ್ತೆ, ರೊಟೇಟಿಂಗ್ ಟೆಂಡೆನ್ಸಿ, ಡಿಗ್ರಿ ಆಫ್ ರೊಟೇಷನ್ ಇರುತ್ತಲ್ಲ ಸೇಮ್ ಆಗಿರುತ್ತೆ. ಒಂದ್ ರೊಟೇಷನ್ ಏನ್ ಮಾಡುತ್ತೆ, ಇನ್ನೊಂದು ರೊಟೇಷನ್ ನ ಕ್ಯಾನ್ಸಲ್ ಮಾಡ್ಬಿಡುತ್ತೆ. ಅವಾಗ ಏನಾಗುತ್ತೆ, ಆಪ್ಟಿಕಲಿ ನಮ್ಗೆ ಯಾವ ತರದ್ದು ರೊಟೇಷನ್ ಕಾಣುವುದಿಲ್ಲ. ಸೊ ಆ ತರ ಒಂದು ಫೆನಾಮಿನನ್ ನಾವ್ ಏನಂತ ಹೇಳ್ತೀವಿ, ಆ ತರ ಒಂದು ಮಿಕ್ಸ್ಚರ್ ನಾವು ತಯಾರಿ ಮಾಡಿದೀವಲ್ಲ, ಆ ಒಂದು ಪ್ರೊಸೆಸ್, ಆ ಫೆನಾಮಿನನ್ ಏನಂತ ಹೇಳ್ತೀವಿ ನಾವು, ರೆಸಿಮೈಸೇಷನ್. ಯಾಕೆ ಇದನ್ನ ಹೇಳಿದೆ ಅಂದ್ರೆ, ರಿಮೆಂಬರ್ SN2 ಮಾಡಿದಾಗ ಯಾವತ್ತೇ ಆಗ್ಲಿ, ಯು ಹ್ಯಾವ್ ಟು ರಿಮೆಂಬರ್ ದಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಗೆಟ್ ವಾಟ್, ಎಸ್, ಅ ವ್ಯಾಲ್ಡನ್ ಇನ್ವರ್ಷನ್ ಸಿಗುತ್ತೆ ನಮ್ಗೆ, ವ್ಯಾಲ್ಡನ್ ಇನ್ವರ್ಷನ್. ಸೊ ಪ್ರಾಡಕ್ಟ್ ಏನ್ ಸಿಕ್ಕಿರುತ್ತಲ್ವಾ, ದಟ್ ಇಸ್ ಆಲ್ವೇಸ್ ಅನ್ ಇನ್ವರ್ಟೆಡ್ ಪ್ರಾಡಕ್ಟ್. ಯು ಶುಡ್ ವೆರಿ ಮಚ್ ಕೇರ್ಫುಲ್. ಅದೇ ವೆನೆವರ್ ಯು ಆರ್ ಡೂಯಿಂಗ್ ಅನ್ SN1, ರಿಮೆಂಬರ್ ದೇರ್ ಇಸ್ ಅ ಪಾಸಿಬಿಲಿಟಿ ವಿ ಕ್ಯಾನ್ ಗೆಟ್ ಅ ರೆಸಿಮಿಕ್ ಮಿಕ್ಸ್ಚರ್. Racemic mixture, very much important tendency. But the important thing you should also remember what, there are three possibilities whenever a nucleophile is attacking our stereogenic center. One is our retention, that is what, leaving group in a position alle nucleophile attack agadu, retention ಆಗಿರುತ್ತೆ. Inversion ಅಂದ್ರೆ ಏನು, whatever the nucleophile is there, it is going to attack your stereogenic center from the opposite side of your leaving group. Finally we will be getting an inverted product, that is called as what, Walden inversion. And third part is your racemization, the phenomenon of converting your racemic mixture, the process of converting your enantiomers into that of your racemic mixture during a reaction will be called as what, racemization. Now I think it will be clear when you go through the examples what we have given you, stereochemistry part of SN1 and SN2. Just I would like to give a note over here. So ಇಲ್ಲಿ ನಾವೇನ್ ಹೇಳಿದ್ವಿ, whenever a nucleophile is attacking your stereogenic center, when the question arises when the nucleophile is attacking the carbon other than that of your stereogenic center, ಏನಾಗಿರುತ್ತೆ, remember, in that case only retention is possible. ಯಾವಾಗಿದು, when our nucleophile attacks the carbon other than stereogenic center, ಆದಾಗ ಏನಾಗಿರುತ್ತೆ, whatever the final product you are going to get, it is with respect to the retention. ಯಾವ ಗ್ರೂಪ್ ಹೋಗಿರುತ್ತೆ ಅದೇ ಪೊಸಿಷನ್ ನಮ್ಮ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಅಟ್ಯಾಕ್ ಆಗಿರುತ್ತೆ. ಒಂದು ಎಕ್ಸಾಂಪಲ್ ನೋಡೋಣವಾ. ಸೊ CH3, here is your H towards the observer, C2H5, one more in a plane, CH2OH ಅಲ್ವಾ. ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀನಿ ನಾನು, ಇದನ್ನ HCl ಜೊತೆ ಟ್ರೀಟ್ ಮಾಡ್ತೀನಿ. HCl ನ Cl- ಗೆ ಏನಾಗುತ್ತೆ, ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಆಗಿ ಆಕ್ಟ್ ಆಗ್ತಾ ಉಂಟು. ಇಲ್ಲಿ OH ಇಸ್ ಎ ಲೀವಿಂಗ್ ಗ್ರೂಪ್. ಸೊ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಈಗ CH3 H C2H5 CH2Cl. ಸೊ ಏನಾಯ್ತು, ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ka position, whatever the position of your nucleophile was there, your leaving group was there itself our nucleophile has come and sit alva. So there is a retention part. So remember, whenever our nucleophile is attacking the carbon other than the stereogenic center, only one possibility is there, that is your retention. But whenever our nucleophile is going to attack the stereogenic center itself, chiral carbon ಗೆ ಬಂದು attack ಆಗಿದಾಗ, there are three possibilities. One is retention, second is your inversion, third one is our racemization. So these two we have seen when we were dealing with the SN1 and SN2, certain examples, stereochemistry examples. Go through once again, you will be clarifying your doubts. Okay.